And there's the here.
Yeah.
I think that's
No, there's one more. There's the Indian guy we walked by that was in the lab.
It's really you. Is he a burst student? So, but maybe that was Stefan's student. Stefan's student, but it's just working.
I think it's Fanny's student who just got hired.
Right. I think
okay.
we're ready to start again. Maybe.
Oh, sorry, you were saying.
Yeah.
Yeah.
So before we took the lunch break, someone was asking me like, how would you check this? So let me like slightly go back and make this a very small system such that I don't break everything. One of the ways that I can think of, which was already like kind of hinted at in this block of text, is that you can check whether the expectation value matches, the expectation value function matches the overlap function.
Yeah, I guess one.
And so in some sense, this would mean if I make a two-side gate like this, so in this case, just 2 times z, I can, if I remember the name of my functions, compute the expectation value of
I'm trying.
Oh.
I think.
Just give it the first 2 arguments.
Right.
Did you take something?
Do you need that?
And that should equal taking the overlap of the state with applying the gate. And I might have swapped these arguments. While that runs. No, still nothing. I will debug this in a second, and then we'll go from there. The idea still holds. So this kind of approach where you evaluate these things either like without any truncation, then the values should be equal up to machine precision, and otherwise they should be relatively equal. I will have a look at my solution.
I just was thinking to myself.
So we need to apply your scheme to give me matrix multiplication.
So I have to merge it and do that. Where against everybody. You sure?
So that whole thing, so yeah, matrix product.
Right. Of course, I was forgetting that this only works for normalized states. So still have to take the, like when taking the expectation value, we divide it by the norm of the state. And so when you take the overlap, you still have to divide by the norm of the state. Does that work for everyone? Does that make sense? Good. So now I wanna touch upon something which is basically the entirety of the games and the tricks that people in tensor network community play. And the idea is centered around a very simple kind of fact, which is just that anytime I'm contracting 2 things, I can insert a matrix and its inverse without changing the result. This is not a deep statement at all. This is just saying that if I insert x times x minus 1, this evaluates to the identity, so you can just put that everywhere. And that trick kind of becomes very important in tensor networks because it tells you that, like, whenever I write down a matrix product state, or any tensor network for that matter, there are degrees of freedom there that don't actually affect the states at the end. And so if I'm able to play around a bit with these gauge of degrees of freedom, I might be able to do some things that help me out. And so in particular, for matrix product states, one thing you can do is you can choose a gauge that either makes my matrix product state tensors left or right isometries. And why is this relevant? If you look at the picture here, is that if I bring an MPS tensor into left canonical form, left orthogonal form, it means that when I contract it with the cat with the bra, and I start from the left, I just get an identity. And so if I just zipper that through my entire MPS, what's going on is that, like, every time I start from the left edge, which is an identity, I contract it with the left isometry, so I get an identity again. So I contract it with the left isometry again, and I get an identity again. And so basically, what you can do is you can transform your entire MPS into a form where everything to the left of a given side is an isometry in the right direction. Everything on the right of the side is an isometry in the other direction. And what you end up with is one single center tensor, which is not an isometry. And one thing that you can kind of think about here is, like, in this form, what would the norm of such a state look like? And this is, if you recall, like, to compute a norm, we just sandwich the thing with its conjugate.
The sum of single values of one is one.
Yes, basically yes. So, and I will make some help, like, drawings on the whiteboard. Let me know if you cannot see them, right? So the idea is that if I look at something that looks this is a bar. So you get the idea here. I have used, let me put the equations on the screen. I can use these equations to simplify this entire computation. In particular, if I look at this part, in this particular gauge, this should be the identity, which means I can simplify this entire thing, forget about that part, and contract like that. Of course, I can recurse. This thing is the exact same equation, and so therefore I can simplify and make this into an identity. On the right-hand side, I can do the exact same thing, and so at the end, the only thing left over is this. Does that make sense to everyone? So we all agree that this is way simpler to compute a norm now than it was before.
I think so.
Because even for a chain which has like 500 sides, I can compute the norm just by taking the norm of the center side. Okay. In a similar way, can you think about how you would compute an expectation value of a local operator? Yeah, it's not a deep question at all. Like, you do the same trick we did before. I add an operator here and everything remains the same. So as long as my MPS is gauged in such a way that the center and the place where I want to apply the operator coincide, then I can very efficiently evaluate this. What happens if I have a two-side operator? Does that drawing make sense here? So one of the choices you can make is you can apply the two-side operator on the center side and to the right of it, or to the left of the center side and on the center side. And then again, everything to the left simplifies and everything to the right simplifies. I cannot simplify this last side because in order to simplify these two to the identity, I have to use the equation where there's nothing in between. And so this no longer holds here. So
What if you want to apply the two gate, the two labels on the two sides that are not
Yeah.
each other?
So we're doing that. It becomes easier to compute.
So like here, part of
I'm going to draw a lot of boxes. So, you know,
sorry.
I don't know. I would assume that if you tap the expectation value times take the Hermitian constant.
Oh.
Just contract that.
Yeah. And you simplify the middle one as well?
so I can simplify this one. Get rid of this. I can simplify this one and get rid of this one. I cannot simplify the middle. And the reason is that, like, in order for me to be able to simplify the middle, if you recall, the equation doesn't just mean that there's doesn't just mean that there's nothing here. It also means that there's an identity on the left. So I need both of these operators. So for longer range things, you still have to evaluate the expectation value of an MPS of the length of the range of the operator that you're applying. Does that make sense? Something else which is important is that because my basis on the left is orthonormal and because my basis on the right is orthonormal, because of the exact way that I've defined this, this means that, like, if I look at the singular values of this center tensor, this is exactly the Schmidt coefficients of the entire state. This is not just the Schmidt coefficients of this local patch. Like, if I looked at the entire state and I made it dense, this would give me the exact same result. And the reason for this is just the exact same thing that, like, everything to the left simplifies to the identity, everything to the right simplifies to the identity, and I can work with this. Why is this important? Why am I telling you this? One of the things that we did before, right here. So when we apply a two-side gate, what's going on here is that I write this out as a new tensor by contracting it. And now I'm going to split it with an SVD back into components. And I'm doing some kind of truncation. And my singular value decomposition tells me that this factorization, this truncation is optimal. As in, this is the best truncation I can do that recovers this original tensor. Why is this not enough? Why do I not just want this? Any ideas? Why, like, what am I missing? the essential component is that I actually really don't care about approximating this thing as well as I can. I actually care about approximating the entire state as well as I can. And so, of course, I can try my very best and truncate this thing in a way that is very good and very well. But if this affects the entirety of the rest of the chain in such a way that everything like conspires and does this in a wrong way, then this truncation is actually horrendous. And so basically what that means is that in order for this whole theorem about this truncation of the SVD to be optimal to hold, I first have to make sure that everything to the left of this is in left orthogonal form and everything to the right of it is in right orthogonal form. A simple way to see this is if I think back about not even about applying applying an operator, the optimal way of truncating a state of itself is by discarding the Schmidt coefficients. And so this, I can only compute the Schmidt coefficients by bringing everything to the left in left orthogonal form and everything to the right in right orthogonal form.
Make sure I understand. So what are the bond dimensions between all these orthogonals?
They're the same. Like I'll get to the get to how to make the left orthogonal form in just a second.
So this might be a dumb algebra question, but if I have the same two-side operator, I could apply it either on the center and one to the right, or center and one to the left, and they should give me the same answer. I can't see that algebra, obviously.
Remind me to come back to this in just a second. Okay. So, I mean, this is all very good. Now the question is, how do you bring something in this canonical form? Like, what is really going on? And so the idea is that we saw how to locally create an orthogonal basis. This is just a QR. And so one of the things you can do is you can start from the edges, and I will make some more drawings. So I can start from the edges and say, cannot start from the edges. There we go. This tensor by QR decomposition is equal this tensor. And this is just, like you apply the left fourth function on this one MPS tensor, and that gives you that function. Then I absorb this here by multiplying it. At some point, I'm not going to close this anymore. And so I just take this extra tensor, multiply it into the next side, and go from there. Of course, this gives me a new MPS tensor, which by QR decomposition, this is the next Q and the next R. And I will stop writing on the bottom here and give it a better thing for you in a second. And just absorb this new R into the next side. And so effectively what I do is I transform this into an orthogonal tensor. I'm left with an R that I then absorb here, which I will then transform into an orthogonal tensor, which gives me an R that I will absorb here. And of course, this is symmetric, right? Like I can do the exact same game here where I do an LQ decomposition, which gives me an L that I absorb here. And I'm left with something which is in the center gauge, because now everything on the left is a Q and everything on the right is a Q. And very often we use triangles to denote this Q with a direction. Is this making sense?
Can you just do this for the center one or
Just that.
did the R's where
Sorry, I didn't catch that.
so that you, for example, you want all the be on the second side, just you can just do that anyway.
You can move this anywhere. You can select any side you like. You have to keep in mind that you have to start from the edges. Because of course, if I just start doing this in the middle, I am left with a Q, but everything to the left of it is not in the correct form. And so if I were to do the entire procedure again, there is an R that's coming from the left that I forgot about. So there's a definite order to this. Yes.
So if I understand this correctly, it's to implement a easier operator on one side, or is that not the motivation?
The motivation is that like I really want my truncation to be optimal, and this will be like.
Okay, because I was wondering, because right now there's a lot of sort of, it feels like you're doing a lot of operations here, right? You first do the composition and then you have to do a contraction and then another composition.
Yes.
I was just wondering, like, how does that compare to just contracting the whole thing? And like, why is it that we are,
So a QRD composition is, again, n cubed. So like the scaling of the entire algorithm is the same. So we can do this in a semi-efficient way. Of course, you want to avoid having to do QRs all of the time. The reason why, and I mean, I can hopefully get ahead of myself a little bit now. After we fill in the exercises, is that like, if you do a truncation, you actually need it to be in this form for this truncation to be optimal. And if it's not in this form, you are truncating in a random basis. And so you lose this guarantee that throwing away small singular values is throwing away small parts of your states that don't matter.
Okay, that makes sense.
Yeah.
So I can see how this maybe would make it computationally easier if you've already done this on the state to do, say, like the norm of the state, where all of your left orthogonal matrices have a pair and cancel out to the identity, and all of the right cancel out. I guess the thing that I don't understand is the connection you made just now of why that makes the truncation optimal. I guess that's not immediately obvious to me why this would make for an optimal, like global truncation, not just SVD within a particular block. Does that make any sense?
Yeah, it does. So the idea of an SVD, or what makes an SVD optimal is you start from a matrix, you select an orthogonal basis on the left, you select an orthogonal basis on the right, and then you have the singular values which give you the weight for each of these basis states, right? And then I'm saying, because this is an orthogonal basis, every single one of these basis vectors like contributes the same amount because it's orthonormal, sorry. And so then the only thing that matters is the weight that's in front of them, which is the Schmidt value or the singular value. This hinges on the fact that this is an orthonormal basis on the left and the right. Why is this true? I mean, you can imagine that if I just multiply this U and this V with a diagonal matrix, which is 1 everywhere and 1 million for one entry. Clearly, if I now, like, I will overvalue the contribution of that specific value. Does that make sense?
Yes.
So then, if I think about my entire state exponentially large, I can think about making an SVD in the center. And so basically what I want to do is I want to select an orthogonal basis on the left and an orthogonal basis on the right, and then discard the singular values in the middle. Of course, in order for that to hold, I cannot just do an SVD of these two sides. Because if the rest of the entire system is not in this orthogonal form, that just doesn't hold. And I think one of maybe the final like small little detail, which is not super obvious but might help, is that if you chain orthogonal matrices together, they remain orthogonal. And so the idea here is this is what orthogonality means. And so basically, if I if I multiply two things that are orthogonal, if this one's orthogonal because it's orthogonal, that becomes the identity. That one is orthogonal, so that becomes the identity. So the A, B dagger is equal to A, B dagger, A dagger. And then if this is the identity and this is the identity, then the entire thing becomes the identity.
So would it be correct to say that by doing this QR decomposition from the edges in, it's almost like we're doing a singular value decomposition of the whole thing in the sense that we're orthogonalizing everything to the left and everything to the right?
Absolutely.
Okay, so it's like a global SVD.
It is a global SVD.
Cool.
Without the exponential cost of a global SVD. Was one more question? Yeah.
Yeah, so reason you're saying orthogonal and not unitary?
No. Unitary is also fine.
Okay, there's nothing like, all these are real anyways, right? Or
in our case, they're real. In the general case, they're complex. Unitary is the correct word. Orthogonal means the same, depending on who you ask. Orthonormal is really what I mean. Yeah.
But they are not square, right?
They're not square. So, okay, technically I need to say isometry, but I don't really want to go into that level. So they're not square, so they're an identity in one direction and they're a projector in the other direction because of the rectangularness. Yes. Yeah.
So is this different than normal MPS? Like you mentioned that if you get the single values, you call it right, and if you get the single values with V, we call it left.
Okay.
So we just keep adding, like, with the left hand side on this side, and then pick the right hand side, and then they meet.
Yep. Yes. So if you think about starting from a dense state, I mean, if you do an SVD on one hand, you are left with a U on the left, which is already orthogonal or isometric. And so then you do the next one. And so again, you end up with a U on the left, which is isometric, but combined with the U that was before that, this is still isometric. And if you do this through SVD, you automatically end up with a gauged matrix product state.
So if you do SVD normal, we still have the orthogonal. It's just that the singular value will be the last side.
Yes, exactly. All right. So then in practice, we can implement this, and actually, like, this is what this entire center field was for. It is to keep track of where in our state do we actually currently have this orthogonality center. Because of course, you don't want to have to re-QR and LQ decompose the entire state every single time you do something. And so basically, as long as you keep track of where everything's going, you can just update small parts of the network and work with that. And so the two basic functions that you need is, well, move the center right by one and move the center left by one. And so you can see here that in order to move it right, I just take my MPS tensor, I QR the state that I have, I leave the Q where it was, and I absorb the remaining factor on the next side. And for convenience, I set the center to be the next side over. For the left thing, which is of course symmetric, I first have to create a new MPS tensor. because I have to LQ in the other direction and my semicolon is in the wrong spot. And so basically what I'm doing here, oops, L, E, talking and typing at the same time, which doesn't work. Is I first, also, can everyone see that, like the semicolon? Is that clear enough? I first move the semicolon from here to here, basically repartitioning the matrix. I then do an LQ decomposition to get to end up with a Q. Finally, I have to reinstate the Q here. So LBR is Q. Right? And I absorb my L factor on the previous side. Does that make sense?
Wouldn't it be LQ of L semicolon PR? No.
Sorry, can you say that again?
When you reassigned, because right now you are assigning CAILP semicolon R, QLP semicolon R, which is just the same. I think the output should come out as L semicolon PR. But no one.
You're right. Thanks. Good eyes. Good. So then in order to canonicalize a full MPS, we'll give it a site. And so the full canonicalization should be move everything from the left to the middle, move everything from the right to the middle, and end up with a canonical MPS. So I'll just give you a couple minutes to write that out. This should be somewhat straightforward.
These things only more than the field progress within the networks would be very bad if you have already moved. You don't want to do that. What you want to do is really on and more than
And that's why he's like, move it all into one, so it's all one non-trivial.
doing this thing, you have this does something, I don't know what, does something such that you don't lose information.
Okay, because it basically
Yeah. Okay.
moves all the stuff into one,
Yes.
and then you would do this thing
Yeah.
there.
Yeah.
And then that's why though you have to move it, because if you want to buy 2 cubic feet somewhere else, then you'd have to be like, scooch it over. That's getting into that.
When I say center, I mean center of orthogonality. It doesn't have to be the center of the MPS.
Getting it into this form.
Sorry, confusing names.
What does it mean? Center equals 0.
The center of orthogonality.
Yeah, so if we thought of all the way to the left. Oh, because we don't index at 0, so this is just like it's
function.
So the question is like, what do I mean when I say gauge? So gauge refers to the fact that we call this gauge degrees of freedom because they don't affect the state.
Right.
And so when I say I have no information about the gauge, that just means that, of course, the state is in some gauge because you wrote it down, but I don't actually know which one, and I have no information about it. It means that like basically I have as much information as you inserting random x minus 1 everywhere. And so now I will fix this degrees of freedom by choosing specifically this gauge.
The right is like a that's also a specific choice.
Yep. Right. So let me write out together what we're doing.
Right.
So the very simple thing is doing exactly what I said, and is we start from the left. We do a for loop going from side 1 to side I minus 1. And we move the center right by 1. And then we do the exact same from the right. And so we start from the end. We iterate backwards towards the specified I, and we move the center to the left. And then finally, now we're ready to normalize our state. Because of course, I just said that the norm of the MPS is the norm of the center tensor. And so here we can properly normalize the state.
We're going from 1 to I minus.
So if you recall, I'm doing a QR on all of the sides except for the center side. Because the center side, like I is the one that will absorb the R from the left and the L from the right.
We have to do one last.
But I can't just run it right to run there.
Get the single values from the right single.
Okay. Okay.
They're already in these functions. So the last step of this move center right function will take the MPS tensor at side I minus 1, do a QR decomposition, and multiply the R into the MPS tensor at side I. And the last step of the move center left will do the opposite. And so the L and the R are already absorbed there. Yeah.
Would I just use an ANDAS which already has a canonical form? What is these?
So we'll do variational optimization in say like 25 minutes. And this is exactly why we're defining this.
Okay.
So one thing you can now do is check and see if this actually matters. Like why are we doing this? And so to do so, like we define something called the fidelity, which is basically just like how close are two states together. And we'll do a little demo where we start from a random MPS. We're going to apply a two-side gate. I've just picked a random two-side gate here, my favorite one, I can exactly apply this. So without any truncation, I can truncate, but use like not use any gauge. So with my random MPS, and then I can canonicalize, put my gauge, my center of orthogonality at the center, and now apply my gate and truncate. And we can compare all of these things together. And if my things are updating, this should work. What am I missing?
You still have the error not implemented in your function that you wrote above.
Oh,
Yeah.
Thank you.
So this function already does the article.
And then also probably
This
two.
The matrix products.
There we go. So if my state is at least a little bit bigger than 4 sides, you can see that if I gauge first and apply and then compare with an exact, I get a fidelity which is significantly higher than if I don't gauge first. And this is precisely the fact that we're truncating in an orthogonal basis instead of a non-orthogonal basis. This ID at least makes sense to everyone. Okay, I'm getting only a small amount of confused faces, so we'll just go from there. Right, and so then there's a little bit more text. And so that kind of brings us to our first actual full-on tensor network algorithm, which is a way to compute the ground state of some local Hamiltonian by doing imaginary time evolution on a random state until it becomes the ground state. So what do I mean with this? Well, if you think about like a Schrödingerian equation where you can evolve this equation in time, you're basically saying that my wave function at a given point in time t is the exponential of the Hamiltonian with factor I times the initial state. And so now if I rotate my time and do imaginary time evolution instead, so I do a Wick rotation, then what ends up happening is that in this exponential, I get minus TH. And effectively, that means that all of the high energy states are exponentially suppressed with respect to the low energy states, which will be which will then remain. And so if I have an initial state that at least has a little bit of overlap with my ground state, I can keep evolving in imaginary time for an infinite amount of time. And at the end of the day, everything that has a higher energy state than the ground state will exponentially die down. And you can make this rigorous by writing it out like this. And if you stare at this for a little bit, then you can see that this should hold. So we're just going to implement this. And the idea is like, okay, how am I going to write the exponential of the Hamiltonian? Because of course the Hamiltonian is a sum of nearest neighbor terms. So if I just exponentiate this, I'm now asking for the exponential of a matrix which is of exponential size, which is not really what we wanted to do. And so the idea is to do something which is incredibly common, which is we will write this exponential of a sum as the product of exponentials. And we're only allowed to do this for small time steps because the error we make is proportional with the time step that we choose. And so this is a first order Suzuki Trotter decomposition. And this holds, like technically there should be plus mathcal O of tau. If I wrote that correctly, where did I write this? Maybe not there. Oh. This is why you don't live code here. Yes. Right. Oops. And so basically what this means is that we're going to split up our big exponential into exponentials of the local two-side gates. And then we're just going to apply them sequentially. And in fact, you can show that you can actually do something which is correct up to second order by doing a staircase system where we're just going to first apply something on gate 1 and 2, and then apply the gates on sides 2 and 3, and then on 3 and 4, and then on 4 and 5. And then we will just do 4 and 5, 3 and 4, 2 and 3, 1 and 2. And if you are very careful and want to do a lot of math, you can show that this is correct up to second order. Of course, why do we do this staircase? Well, if I do a local gate application and now I just have the center between like at side 1 and 2 or at side 2, I can do one gate application and then move over my center by one side, and then do the next gate application and then move over my center by one side. And I never have to move the center by an extended amount of sides. I just keep everything local and just move over one to the next. And then if I apply this an infinite amount of time, but in practice a finite number of times, you should obtain the ground state of the system. So to do this, the first thing is we need to define what are our local gates. So what is our Hamiltonian like? We had single side operators and two side operators. We can do a trick where we will pretend that the single side operators are also two side operators by just absorbing them. And you can see this here. This is a trick where we say, I absorb x times the identity plus the identity times x. And then, of course, I have to divide by a factor 2 because otherwise I'm counting them twice. I have to be careful at the edges such that, of course, at the edges, there's not a neighbor to the left or to the right. And so there, I don't actually have to divide by a factor 2. Does that make sense? Okay. So then I can define the energy, which we will use later. So first things first, we'll trotterize our Hamiltonian by building the small exponentials of every single one of these terms.
Like the nearest neighbor.
Sorry?
Method just works for that kind of Hamiltonian,
yeah.
Nearest neighbor.
It needs to be nearest neighbor. You can do next nearest neighbor as well. You can push it a little bit further, but like this is more for nearest neighbor. Because it builds on this functionality that we can apply a nearest neighbor gate and truncate back down. And so the idea is to first, compute all of these gates. Note that the exp function takes the exponential of a small tensor, so you can use that. Then we will do one single Trotter step, which just means go from left to right, apply the gate with the functions that we already defined, move the center with the functions that we already defined, do the same to go from right to left. And then finally, because we are evolving in imaginary time, we are projecting out the high energy modes. So we're losing norm because we're projecting them out. So we will renormalize at the end of our scheme. And I'll give you, let's say, 5 to 10 minutes to do that, and then I'll continue from there. When you say efficient, what do you mean? Sorry.
It's local. And two sides that we act on is all we care about. There are like much of other something that I can shut up.
Yeah. I mean, in principle, like one of the things you can always play with any of the tensor network things is that you can swap the qubits by applying a swap gate. doesn't correspond to changing the tensors because you need to, if you swap the physical sides, you need to keep the connections. So basically what you do is you build a swap gate, you apply it, and so now you've teleported the qubits until they become local.
I see. But then, yeah, you would have to apply n swap gates to each.
The DMRG implementation we have, where we will build, can handle longer range things. I'll show this at the final time. There, the idea is that here we're really we're trying to approximate a local shape applied through state. The alternative is to consider the entire operator as a whole and do some global minimization on that. So the algorithm is a little bit more complicated. We need a little bit more time for this. Symbiotically, yes.
Trying to figure out what to do with that.
I think it might just be cheating and looking at our solution, but yeah, it might just be they named it that because you do like that, but it's not up to you just say,
Oh.
so
You do the gates.
but you're passing the full gates, but it's
Gates have the gate. Square root of a gate. What kind of unhuman matrix square root is?
How many times step percent?
the taco. I think it's really cool. Exponential with finest possible exponential.
That has the C5 as exponential maintenance.
Not gonna lie. Okay, well now I know that tau is the U. This is great knowledge.
The Unicode emojis they can order then.
Yeah, if you so I typed in TAO and autocorrected to taco, and it just gave me a taco emoji.
Oh, that is
Yeah.
His gates have just from the Trotter takes the Hamiltonian and breaks it into the two-side gates. The gates half, I think, are just the two-side gates.
Yeah.
on down.
All right. So let's see and reconvene. Making the Trotterized gates is a simple mapping of take each of the local two-side gates, multiply them by minus tau, and exponentiate them. Why can we exponentiate this? Because it's just a single, because it only acts on 2 qubits. This is a 4x4 matrix. So you can exponentiate this with your favorite matrix exponentiation algorithm. And because it's a 4x4, you can either diagonalize or whatever numerical tool you like and do that. And we do this for n-1 bonds, because we have one less bond than we have number of sides. So then a Trotter step, what does a Trotter step look like? Well, we go from left to right, we apply a gate and we truncate. Then we move the center one step over to the right, and then we apply a gate and truncate again. And I think this has to be +1 actually. Oh, yes, like this. Gotta check the conventions in the move center right function. We want to end up with the center on site i+1, right? And so we just apply a gate, truncate, move the center, apply a gate, truncate, move the center. And we go from left to right and then from right to left. And then at the end, because we are like our center is what carries the norm, we can normalize that tensor. And this is the entirety of a Trotterization scheme, which you can use to compute a ground state. And I think for this, in the interest of time, I'll just fill out the entire function, which is nothing but repeat this entire thing multiple times. And so the idea here is that I start with a little bit of boilerplate just to define a bond dimension that I will use as a maximal cutoff. And then I take time steps that are decreasing in size. Why am I doing this? Well, in the beginning, I want to take big time steps, which, okay, will have a larger error, but I don't care that much because my state isn't very accurate to begin with. And then as I get closer and closer to the ground state, I care more about accuracy, and I reduce the size of my time step and take more steps. And so here you see I will do 100 steps at time step 10 to the -1, 150 at 10 to the -2, and another 150 at 10 to the -3. You can write down more checks on when to consider things as converged, but basically you just apply these gates. Interestingly, I mean, this will not actually affect the result, but if you really want to be correct about it, if you want to do a time step of tau, because we're going back and like forwards and backwards, you have to apply gates that are tau over 2, because you're applying 2 gates per bond. And then, of course, because things don't work, what did I break?
If you missed n equal length of C sum up in the previous one.
Thank you. If everything goes well and this is loading, which it isn't. Oh, there we go. So with this scheme, our TEBD, I mean, at least at a site, at an MPS for 8 sites, actually does reproduce the dense energy values up to 10 to the minus 6. So now the question is, of course, does this scale? Because of course, 8 sites is cool, but we don't want to be doing 8 sites because then we could have done exact diagonalization to begin with. And so the last part of this entire notebook, you can look through a bit and it has some plotting machinery, is just, can we do this on larger systems? And there's some sliders everywhere you can play around with. And so here you can see that on a chain of 50 sites, this gives you this profile. And very importantly, you can see that the entanglement across this entire chain remains bounded, which means that we can very efficiently simulate this with low bond dimension states. Right. Does anyone have questions for this? So let me give a slight recap before we move on to the next thing. So basically, the idea is that we started out with large tensors that we were going to represent in a factorized form, right? Because as we factorize them, we can reduce the number of parameters that we need to represent an exponentially large state. We then kind of were like, okay, let's have a look. We create a matrix product state as an example of how you can do this. And the entire point is that, like, if you do an SVD in a correct basis, you can truncate very accurately by throwing away small singular values. In order to do this correctly for a matrix product state, that means that we play around with the gauge degrees of freedom to make sure that everything to the left is orthogonal, everything to the right is orthogonal, and now we can locally manipulate our state without having to do any manipulations on things that are far away. And we can do truncations that are globally optimal. And then we can play around with a variety of algorithms that have very low polynomially scaling cost. In general, all of these things scale cubically with the bond dimension. And this gives us the ability to represent a large variety of ground state physics just with this formalism. Importantly, very importantly, this only works when the entanglement is limited. Because of course, if the entanglement is large, then our truncations are heavy and we will never get the original answer correctly. And then 1D, for local systems, we have some theoretic bounds that claim that this is always the case for gapped Hamiltonians. I think the next thing I will go over is DMRG as the workhorse of all of 1D MPS, but I will give a small bathroom break for this. Yeah.
I have a general question about applying 2-qubit gates.
Mm-hmm.
If it's an entangling gate, do we know how the bond dimension will increase? Like, does it become double or?
It depends on the dimension of the physical space. So for a qubit, the maximal it can become just by looking at the dimension of the arrays involved is the physical dimension times the bond dimension. And this follows from the fact that if you merge the two sides together, on the left-hand side, you have one virtual leg and one physical leg, and on the right-hand side, the same. So the maximal amount of singular values there is virtual dimension times physical dimension. I'll start at 3:25 unless everyone is like, okay, let's go. We'll dive right in.
No.
Yeah, no, you're right. I forgot.
Yes, anyway.
Just saying if you're going to fit the. That's beautiful.
I can't do this sometimes.
Starting from scratch.
Now I think I spent enough to solve this.
Which one?
To solve what was there.
Oh, okay.
I don't know why the things work. But you know that they have to work that way. So this will make sense.
Yeah, unless everybody makes sense, it's a lot.
No. I can tell you a bit about Mara if you want. The story starts with, I think at this point in time, there might be 2 people in the world that are related to Mara. Yes. So I think it's one of those things where, I mean, it might make a comeback for a variety of reasons, but it's, for those that are listening that don't know what Mara is the idea of, like, instead of doing a linear chain of MPS tensors, you have this hierarchical structure of tree-like nature that you keep piling up. And so the reason why this is elegant, or why people were excited about this, is because this kind of naturally encapsulates some scale invariance. Because as you zoom out, you just go up in the tree, and so you have some resemblance of that kind of notion. The reason why people do this is that MPS are known to capture gapped states perfectly. And so for gapless Hamiltonians, you normally need logarithmic correction to the entanglement, and so principally you need infinite dimension.
What's happening where?
For
the same.
I think that the claim is that a gapped Hamiltonian has a ground state that is exactly representable as an MPS with finite. For a gapless Hamiltonian, I mean, you can reformulate this in a variety of ways. For a gapless Hamiltonian, this is not necessarily the case. And so Mara is one way to capture that. Unfortunately, it turns out that if you just brute force an MPS, this is a lot more convenient than trying to deal with in practice.
They did?
Yes, so critical phenomena is gapless. But the point is that, like, extrapolation techniques with MPS tend to be more pragmatic than capturing the critical states directly. It's also, I mean, we'll see here, like, DMRG is unreasonably fast and unreasonably effective. Like, it works, it has no business of working this well.
You would think just like
And so
population.
it's very hard to beat, which is a very frustrating thing in research. Like, this is the easy thing that people have been doing forever, and we basically don't really know anything better. If it works, there's nothing you can do.
More of it's right there.
It's not.
Between what you MPS
But I guess it's so close to the Europe that
I mean,
yes.
Yeah, it is quite good.
they're all designed with primary purpose in mind. So Mara was designed specifically for this critical scale invariance type of phenomena because the network itself reflects that.
Oh, that's what I see. That's the
MPS is just for linear chains, PEPS is for 2D chains, and the idea is that an MPS carries an area law, carries states that have an area law in 1D. PEPS can represent states that have an area law in 2D. And then Mara capture the logarithmic correction in an area law that you need for critical states in 1D. It is the bottom line. In the end, DMRG tends to be incredibly effective to the point where even though you need an exponential bond dimension to capture 2D phenomena, a lot of research is happening by snaking a 1D chain on a 2D grid. And not to say that apps doesn't have its own merits. Like, a lot of research with apps as well, and I would say that it's getting more and more active in the last 3 to 4 years. Because it's also like the computational cost is just a lot higher. And so it has the same flavor, like once more computational power becomes available, it unlocks
If I just didn't think.
things that we can do with it. And so
I guess I just like
it has a bit of the same flavor of machine learning where at some point the reach a critical amount of computational power suddenly becomes something that you can do.
But yeah, it's
Something along those lines. So there are two ways we can deal with 2D systems, like you said. One is snaking around and one using PEPs. And both have their pros and cons. Is there a comparison between these two? So dealing with 2D systems?
And I think the reason why it's not directly compared that often is that the more popular way of doing PEPs, and you can do this with MPS too, actually formulate these things directly in the thermodynamic domain. Basically, what you do is you tile the same tensor over and over and over, and you work in that formalism. And especially for 2D, it turns out that this is a bit more stable to work with than actually finite size systems. And so it's a bit hard to compare because then, like on an actual 3D grid, you can snake anything because the bond dimension scales with the width of your system, which is now infinite. Finite size, people have compared them, and I think that's like there is just this thing where like if you go to large enough grid sizes, you will beat the MPS. But that doesn't mean that you cannot extract useful physics from smaller systems. So which thing to choose depends a lot on the system you want to study.
So there might be a system size where you will transition to using PEPs instead of snaking.
Right. 27, let's go. So the final real algorithm that I want to talk a bit about is, and I briefly mentioned this, is DMRG. And DMRG is in some sense the thing that has made tensor networks popular and great in the last 25 years. I might be off by 10 years. Look at that. So the idea is that this is an algorithm that was invented, and it wasn't really originally invented as like an MPS algorithm, like a matrix product state algorithm. But then afterwards, and I mean, you can read through the history yourself a bit. Afterwards, it turned out that like it is in fact completely equivalent to doing a variational minimization on the manifold of matrix product states. And so the idea here is that DMRG really is the thing that you want to do if you care about a ground state, and it works incredibly well. And it builds on some of the notions that we had for the TEBD, like which is the previous algorithm we had, but kind of bypasses the notion of imaginary time evolution altogether. And in some sense, there's some theory that actually shows that this is in fact just doing imaginary time evolution with infinitely big time steps. So you can kind of expect that this works better because of that way. I will try and make this a little hands-on and a little just explanation and keep an eye on the time. But feel free to like stop me when things are not clear. There's a bunch of like interesting steps there. Some of them are less interesting and are just technical. So I will skip over them a little faster. but like, don't worry if it's not clear, right? Feel free to stop me. Right. So because it's a new notebook, I will copy over a bunch of stuff from the old notebook, just so we don't have to deal with that again. So we have a local dimension, we have the operators we need for defining the Hamiltonian. We have an MPS, which is just a vector of MPS tensors, a number of utility functions for working with this MPS, and then finally a number of utility functions to work with the gauge of the MPS. In one of the reasons why people like the Ising model is that you can map it to free fermions, and therefore there is an analytic solution for the ground state energy. I've included the way of computing this so that we have something to compare to at the very end, even for systems that are larger than ED can reach. The first thing, which kind of alludes to some of the questions that we've had a number of times, is that we kind of in general don't want to restrict to nearest neighbor gates. We want to be able to work with Hamiltonians that are a little bit more generic than that. And the entirety of that like field is, well, maybe we should write our Hamiltonian as a tensor network itself. And that is the natural language of working with operators in this framework. And so similar to how an MPS is a matrix product state, we can make a matrix product operator just by tiling these now four-leg tensors together to construct the so-called MPO. And again, I mean, I have some convention for the leg order. You can pick whichever you want. For the purpose of this, just use this one. And so now, of course, the question is like, how do I go from a sum of local terms into something that looks like this W? Like, how do I fill in the entries of this W? And there's a very fun trick, which boils down to finite state machines. Like, who has not heard of a finite state machine? Okay, so a finite state machine is a kind of system in which you have, unsurprisingly, a finite number of states and a different set of transitions that allows you to go from one state to the next. And why is this interesting? Like, if you think about this sum of local terms, you can think about going from the left to the right and keeping track of all of the things that could have happened. And so if I start all the way on the left, I am in one state which basically says, okay, nothing has happened yet. If I then go to one side to the right, there's two things that can happen. Either I apply one of the z terms, meaning I apply a z, go to the next side. And so this is one of the possible next states to be in. I can also apply the x and go to the next side. This is a different final state to be in, because afterwards we'll have to do different things. And then the other thing is that I can do nothing, just apply an identity and move over to the next side. And you can kind of think about tiling this as you go along. So then if you look at the second side, you can be in three states. Either nothing has happened, in which case you can either apply an x, a z, or an identity. I can have already had an x, in which case nothing can happen. I only will have identities afterwards. And then finally, if my previous thing that I did was apply a z, I have to apply another z because I had the two-state gate. And this entire thing can be encoded in a transition matrix. And if you squint at it a little bit, you can see that if I map my three states as ready, half applied, and finished to the rows and columns of this matrix, you will see that if I just multiply this W matrix together a number of times for each side, I will in fact sum the entire Hamiltonian again. This is completely not obvious, so I would advise you to write this out, write out 3 of these W's, do the matrix multiplication manually, and see what comes out. And you will just see that exactly the sum of all of these terms come out. And this is kind of the fancy trick that we're using to map this to an MPO. Yes?
What determines whether you're applying a G, Z or an X or?
You need both.
Okay.
Because you basically, you want to build a machine that enumerates all of the possible all of the possible terms in my Hamiltonian. And so, excuse me, if you think about what matrix multiplication does, is it connects one row with one column, and it will just sum up all of the possibilities of these combinations. And so, in that sense, it is exactly that part that will generate all of the sums out. Are people okay with accepting this, or do I quickly write this out on the blackboard or the whiteboard? This is not a very interesting, deep result, and you can just try it out yourself, or you can just believe me.
We can believe you.
Can believe me? Good, great, because I'm not sure I can actually do this on the whiteboard without making mistakes. Anyways, so putting that into code, you have to do a little bit of index manipulation to create a tensor like this. What I did here is my first and last index of these 4-dimensional tensor. Boil down to the rows and columns of this matrix, and the 2 middle ones boil down to the physical operator things that it's acting on. So what I'm doing here is I'm saying that the first row and the first column will act on the physical 2-dimensional space via the identity. And you can see here that I've inserted the identity matrix. Similarly, the second row and first column, if we recall here, has to be a Z. The third row and first column has to be minus G times an X operator, and then we fill in all of the remaining things to create the tensor. The only other thing we still need in order for this MPO to be full is that we have to keep in mind that on the boundaries, of course, I don't have a matrix. I have to put in like this one boundary condition, and that is what's happening here. So now what is the ID? I can write down the expectation value of the Hamiltonian, or also known as the energy, by sandwiching this MPO in between the MPS and its conjugate. So I now get this triple layer object. And if you think about this, we'll skip this in a second. It's again the similar statement where if I wanted to compute this value, which is a scalar, I can just start from the left and snake my way through this entire network and just contract from the left to the right to obtain the energy. And so here I have some utility functions for starting that. We can skip this exercise for now. I'm happy to come back in a second. But what's important about this construction is that you can also do next nearest neighbors or longer range operators in this way. And you can think a bit about constructing a finite state machine that would generate that if you want to. Yes.
Constructing the MPO, the one dimension here is 3.
Yep.
That's because we are considering the nearest neighbors.
Yep.
So if we add neighbors on that.
Yeah. So in some sense, the bond dimension of the MPO is determined by how many operators are going to act in between these two sides or in between these two halves at the same time. So for a nearest neighbor Hamiltonian, well, there's basically only the state where everything is happening to the left of this. There's the state where everything is happening to the right of this. And then there's one operation that has to go between the two. And so these three different options give you at least three, like you need at least dimension 3 to capture that. For the next nearest neighbor case, you get 4 options. And this is again something to think about. And then, so we'll leave this open here. Homework, let's say it that way. I think it's in the solution. So what we really want to do is we want to find a ground state. What is a ground state? Is the state of minimal energy. And so you can just write down what that means. So I want to minimize psi h psi, the energy, but I want to add the constraint, of course, that my state is normalized. Because if I just, like I can make the norm of this thing arbitrarily small, and then of course the energy will go down, but that doesn't really mean anything. And so you can go through the math of how you want to do this. And so you add some Lagrange multiplier, you minimize, you take the derivative, and you end up with some equation. But there's a key thing that is incredibly important, which is if I forget for a moment that I'm allowed to vary all of the tensors in my MPS and just focus on one, then actually this entire equation is just quadratic for any single side. And so basically what is going on is that I can project this entire thing, like if I, for a moment, I think that all of my MPS tensors except for one are completely fixed, I can project this equation, find out what it means for this single side to find the optimal ground state, and then solve that equation by itself. And because it's quadratic, you can kind of see that like the only place that this is appearing, like this MPS tensor is appearing, is like once in the bra, once in the cat, and then the same for the norm equation. You can find out that actually this just gives you a generalized eigenvalue for this localized tensor. And what is even further important, and this will let me put my drawing on the screen in a second, is that if I now go to the correct gauge, well, like let's have a look at where this generalized eigenvalue equation is coming from. On the left-hand side, the only thing I did is just project this entire equation with my MPO and all of the MPS tensors fixed on the left and right, and I just contract everything except for the ones the tensors that I'm allowed to vary. On the right-hand side, I do the same for my norm network. And importantly, the norm network where I don't have an MPO tensor in between, if I now go to the center gauge, this completely vanishes and like all of this environment tensors simplify, and the only thing that's left there is my initial tensor. And basically what this means, long story short, lots of algebra later, is that I can project this entire equation for a single side onto an effective equation for one MPS tensor, which is just finding the eigenvalues of this local operator. And so what does this local operator look like? Well, basically, like if you recall, I'm starting from my triple layer state. I'm keeping everything except one side fixed. And so this is, I want to contract everything but one side. And so that means that on the left, I just have this triple layer thing contracted all the way to the one side. And on the right, I have this triple layer thing contracted all the way to the one side. And I just end up with these 3 tensors that represent the entirety of my Hamiltonian acting on this network. And so what is happening on the left is just, I define, like I come from the edge and I just take this environment and move it all the way over. And I'm doing the same from the right, where I start from the edge and I just absorb tensors and tensors and tensors all the way to the center. And finally, I end up with this effective Hamiltonian that is acting on the state. This is going to get a little bit clearer in a second. We're going to start with a little bit of exercises, which are simply just writing down these equations. And so basically what I'm asking for here is grow left is implement this tensor contraction. Grow right is implement this tensor contraction, and then we'll go from there. Oops. And I might cut this short in just a second in the interest of time. Sorry? Oops. One way of thinking about this is that you have an L for every single site, which just represents the entirety of everything that is happening to the left of it. So you can recursively define L2 in terms of L1 and L3 in terms of L2. Let me make the drawing actually.
But here is definitely the site we are focusing on to
let me make it. Oops. Now I'm going to. Yes. So the idea here is that I have a red side in the middle, which is the one I want to focus on. And basically what I want to do is I want to contract everything but the red side. And so explicitly what I can do here is I can start from the left. And this is just the same thing that we did last hour. And I say, contract this thing. This is now a new tensor. L. And then L prime is contract this thing, which is now a new tensor, which I will then call L again. And then L prime, which is the next L, is this thing. And so I can recursively contract the entirety of this network, and all of the cost remains bounded, cubic in both directions. You're looking at me as if I'm speaking really weirdly.
Do we do this for every site?
Yes. But
that's efficient.
We are doing this for, we're doing this for one site at a time, and we're not going to like it's the same as the orthogonalization procedure, but we're not going to repeat this all over again all of the time. The idea is a bit that if you think about this, you're contracting the entirety of the system that you're not going to touch. If I now do a local change, I don't actually have to recompute this entire system from scratch. I can just keep them in memory. And the only thing that I have to recompute is the things in the region where I touched them. Yes.
So like this is, I can see like the efficiency, but like, what information is kind of lost by doing this process?
This is exact.
Okay, because it's orthogonal.
We're not truncating anything. And this is one of the properties that makes MPS very nice, is that you can exactly contract this. So this is exact, yes.
We start with the specific gauge.
We will bring the center gauge there. And the reason is that perhaps stays. I can draw the same thing for the norm network, right? Looks the same where
This is for looking for like ground state level.
Yeah.
So in principle, I will need both. Of course, if I bring the MPS into the correct gauge, I don't need this at all because this thing simplifies just the loop.
Norm can be found sufficiently, that's what you mean. Okay. But for this part,
of the energy of the room.
we will still have to do this in a radial. Okay. And what if I also have my Hamiltonian in that sort of gauge form where I do QR of each W?
You can do this, but it doesn't make a difference because
or they are not inverse stuff.
Well, the thing is, like, I mean, imagine that I start from this thing and I map it to R, right? What this buys me is that if I multiply this with Q dagger, it becomes the identity. They never have to do this.
Right. We have different.
Yeah.
So when we start with an MPS, we are putting a truncation to the max bond dimension, right? In this case.
Yeah.
And once we have fixed that, then there is no approximation.
Yes.
Okay. And then once we do the DMRG procedure, we get a state like the ground state outright with particular energy.
Yes.
And that state also has the same bond dimension that we fixed at the.
A priori, yes. We'll see some metrics, but yes. So in this case, we're going to start from some fixed bond dimension. We're going to find the MPS of that bond dimension that minimizes the energy with DMRG. And then finally, we'll talk about changing the bond dimension.
So it's kind of like once we fix the bond dimension, we have a certain number of fixed so-called matrix plotted states in that set. And we are going through that set and finding the one that minimizes the energy.
Yeah. I mean, you can think about the entire Hilbert space as one big manifold. And then the manifold of matrix product states of a given bond dimension is a submanifold in that. Yeah. And now we're going to walk over this submanifold and find the point of minimal energy.
I have a quick question.
Yeah.
So like, okay, so in this like instance, this is also like this is time dependent, right?
No. My Hamiltonian is fixed in time.
Okay. Okay, then my question doesn't matter.
You can do this. I mean, you can do things with time-dependent Hamiltonians, but won't be covering that today. That's okay. I'm happy to discuss afterwards.
Expectation values so you have the Hamiltonian and then the wrong test of your state.
Yeah.
And so that's all fixed. So what you're varying is
I guess I'm going to the next step. Like, can we do this discretely? Doing this like incrementally in time.
But it's your terminal on one side. You need both sides.
And then, because I'm trying to see like
you require
does this
both sides of, like,
dynamically, how
when
does
you make a
this
cut,
picture
you need
change
orthogonality on both sides.
when you're thinking about like you know the physics that actually happens, not just like one. So for example,
Yeah,
like,
so
what happens
if you
when
put it at the end, the tensor you're left is a 1x1 tensor, which is exactly the norm, or the square root of the norm. It is if we are only interested in
Generate, right, so if
Yeah.
you have to generate energy levels, for example, they're splitting because like. How does that change? I just want to see like what the dynamic is.
Your operator set numbers in the actual Hamiltonian, the tensor set of
The goal is to find, what we're doing is finding the ground state, which is not a time dependent.
a symmetric one that's like a reflection of each other, so that I only need to.
I mean, unless you have.
The other have the same as this one.
You mean in some sense take the square root of the
Yeah,
Hamiltonian?
kind of.
Um,
W, not the whole Hamiltonian, but each W.
the problem is that you're now looking for you're looking for the square root of an operator that's I agree that like you would like to take the square root of this W, but because there's still the connections in the horizontal direction, that doesn't actually work out the way you want it to. And in fact, if you take the square root of the Hamiltonian, you will end up with an object that requires exponential multiplication.
Created a vector of t steps.
It's the same for like inverses and exponentials in particular become dense.
State energy sort of as a function.
All right, so the contractions for these things are just a matter of, like drawing them out, writing down the indices. So I'll skip over that for now. Oh, and well, this is the action of the local Hamiltonian, which I apparently already wrote out. So I'll fill this out as well.
Notebook.
And so then we have all of the components to actually go and make one step of our DMRG algorithm, which is just a matter of locally finding the eigenvector of this this projected operator. So recall, we contract the entire left half of the network. We contract the entire right half of the network. We get this effective operator. We will now diagonalize this, and we've done this before. We've done this in the first session.
It's not always a planning form.
And this can be done with a Krylov eigensolver. So you just have to apply the action of this Hamiltonian, and this will find the local minimizer of this function. And then finally, like we can do this for one side. And this gives me the optimal solution for this one side, given that everything else is fixed. And this kind of motivates the way that you can continue from this. Is just, well, what if I just sweep through all of my sites and first optimize this site, and then now with this optimized site, I assume this is fixed and optimize a different site. And because every time I do this, excuse me, do you mind waiting for just a second? Thank you. If I optimize one site and then optimize the next site and then optimize another site, because I'm always finding the minimal solution, given that everything else is fixed, if everything continues, at some point, we're hoping to find the global minimum. And as it turns out, if you just sweep back and forth, you will in fact find the minimum of the global system in almost all cases, except when it doesn't work, but let's ignore that for 1 second. And so the entirety of one DMRG sweep looks a lot like this TEBD algorithm that we did before. We make sure the center is at the site we're looking at. We compute the local projection of this entire equation. We solve this local equation, and then we move on to the next site. And again, why is this important as a concept? This is exactly what all of the tensor network methods end up being. You project things to something you can locally solve in a restricted sense. You solve this small equation, and then you move on to the next site. You repeat, you sweep over everything until things converge. and you go from there. I need about 30 minutes at the end to talk a bit about symmetries. I would say to give you about 15 minutes to try this out. Ask me some questions if you want, and then we can go over some of the payoff and the results in the end. Does that work? Yeah. Don't hesitate to ask questions if you're stuck.
I know that when for me, I don't like
you can ask questions like the global.
Oh, yeah. Anything that is who have different
So if you look at the Schrödinger equation, this is the thing that gives you time evolution, and there's a factor I in there, which means that real time evolution gives you exponential with an imaginary minus IT in there. And so if you want to do imaginary time evolution, you have to replace E with IT.
But I just want what they're at. So I say the like some sort of symbolism internet. So it is also testing the flat state of a time dependent.
I mean, it depends a bit on the question, right? Like the ground states of the Hamiltonian is a little bit weird to define because you're asking for something that is the stationary state. So you're asking for a state which has to now vary in time. And so you can look for steady states, something that varies in time. And this can give you approximations, but this would definitely not be the way that you do this because you're, well, effectively what's going on is that as long as your time steps are larger and the scales of the dynamics are small enough, what you will end up with is you're evolving because of the approximations that you're doing, you're evolving with something that is more or less the average of the time. So this will not work and give you what you want, presumably.
No. So I've gotten this right now. So let's say 15. How have I done this?
Well, people do this on 10,000 sites. 10,000. Because everything scales linearly in the chain length. So, I mean, if you run 50 on your laptop, that means that if you can get a supercomputer, you can just run this on 10,000 sites.
So, for example, for this, use tensor network to do the estimated D wave.
Yes.
I want to see these these things they can do it from that top very fast. But this method is
so this method is exactly TEBD,
okay,
but on non-1D geometry. So you get a little bit of extra theory because gauging things on not a chain is harder. This is the propagation and this boundary MPS methods. But otherwise, this is basically the same setup as that. I mean, I think like in that context, it's typically called simple updates, but it's the same thing.
So let's say this is some
Like why this is dynamic? So like where is the information that you have minimized? Yeah. This is also
It says this.
This is here.
Oh, maybe the price.
Oh, sorry. So it says that ASB is left physical right.
Then have a field.
That is right physical.
But I think based on what
It was before all the.
it has to be this way, right?
Right, so I think this should be right physical left. Unless there's a different way to make this guy, but L is B prime W B, so it has to
Actually, this system actually is states in the full exponential. So this is not a one-dimensional function. In some sense, it really is a two. It lives in two together. It's a subcategory of that, but it really isn't that. So I'm not entirely sure if the following is. It's not
the same thing as W.
It's not the case where you can think about this.
The AI didn't quite understand this when I wrote it. I don't think.
So sometimes it's hard for me. And then different directions.
This way.
Yeah.
W would also.
But you look at this thing.
I don't know what order.
Anyway, you're doing. Another way of thinking about this.
I think
really
this is what was envisioned.
Represents X, Y.
I mean, at the end of the day, it doesn't matter what the problem, but
Yeah, so that's why we just to make sure that things make sense. What is
left is the left environment.
Unless
so A is the site that we're working on and then A bar is the corresponding site from the bra, and then W is the corresponding site from the Hamiltonian.
I checked. I no shot that I'm writing this myself. Yeah.
We can call them whatever.
So W cat A bra here.
Right. Yeah.
And These indices are basically up with convention. Makes sense.
Okay, thanks. I appreciate the clarification. It's good to know that I wasn't just missing something.
Yeah, I feel like as long as you're at least in terms of the notation, as long as you're consistent with the variables that you use, it's gonna work.
Yeah.
Even if you have to switch these two and swap these two. No, as far as the convention you use is consistent.
Yes. And this will
give you AWM plus BS. This whole thing gets cut back.
Right. Okay. Thank you.
No. Go with the penalty.
And remind me your name. Shreyas. Jacob.
I know we've
I don't know. I have a hard time remembering things.
Yeah, sorry.
I'm gonna write that down. His name is slipping out.
Basically asking like, okay, what is that?
Zeta and S.
Zeta and I forgot their names.
This 1D layout is just a way of.
So I played ping pong with him yesterday.
Like to work with. But it's less like it is still like you did something with
So
all of the nodes together and it's all of that was.
Oh yeah.
Like I mean, this just represents a different state. You change some of the environment.
There was some confusion about indices.
But I think it's like it's basically just convention tries to decide which these corresponds to which ones. I think it's when you do but I just have to run
Shreyas agrees that these indices are to convention.
Yeah, and I feel like it's stupid to say like first index is not the top one, but that's just me. I don't read like this, but like true to just say.
It's kind of weird. You know, I guess as long as you do it the same way every time, it doesn't matter.
Especially with contraction indices.
Well, one of them will be suppressed and the other one will not. Just evolve.
The confusion in the solution was that they did order was B prime WB, which I guess is the order that you would write it. If you were writing raw operator tet, then you would write B prime WB. I bet that's why it writes it. What do you mean the operation goes like that?
It doesn't, that's also like you. I've done this like this, right? But if I was doing QN.
He's not the R
first, then you would have like.
Not in that
Yeah, some wave
R
function.
is there, but
It's not here, not here.
Wave function of Hamiltonian.
Also here. R is so
You would do something that on.
I would, like, this is the order,
I guess the computer, that the AI that wrote this notebook is conceptualizing it like this right off the bat.
not there.
I think that's
Vector transpose matrix first.
I suppose that makes sense. That's true.
there's something to be some.
Yeah.
They have swapped all.
Certainly not 650.
Said it seemed like it wasn't internally consistent. Right, like it seems like the order for L was not the same as it should have been for W.
Sorry to keep doing that. It says LB prime WB is raw MPO, which is consistent. Does that make sense?
Yeah,
it's just going bottom to top.
Sure.
Yeah. It's kind of like the forever argument between engineers and physicists about like the one can't.
So any function of the discrete set of inputs.
Yeah, as long as it's 1 over square root of
That's so first. It's actually, it's like, actually, no, I'm going to do 1 over the reverse one.
A lot of people do 1 and 1 over 2, right?
Yeah. It is very then what's the generalized I guess you could do 1 and 1 over 2 pi to the end.
Give me a moment, I'll continue a little bit.
One of the spaces just ends up getting
get some results
big in higher dimensions. Like not hard, like these.
Yeah, no, I get it.
Is always disagreement.
I feel like I keep switching between. I don't even know.
The sign is different between engineers and physicists. There's another that's also different, and it's which letter you use. So you might as well just run this, and that reconciles it. It's kind of like two wrongs make a right.
Right, so in the interest of time, let me try and go over the solution line by line. If you didn't get there so far, I hope that I can at least explain a bit about what's going on. So the idea is, again, very similar to what we did in TEBD, is we're going to sweep over our lattice. So we're going to start at the left, do something locally, move to one side to the right, and go back and forth. And so the first thing I do, and I think I renamed the function a little bit, but the first thing I do is I put the center all the way to the left. And then the next thing is that, okay, I will have to do this local application of my effective Hamiltonian. So I want to compute all of the tensors that are on the left, and I want to contract all of the tensors that are on the right. And so, of course, let me say something about the left one first. Well, I am at the left side, so there's nothing on the left. And so really the only thing I can do here is put an identity there. And this was this helper function that was defined before. So all I'm doing here is, if I point at my thing here, this is a trivial 1 by 1 by 1 tensor, which carries one number, which is 1. And so then, after I've done the left side, I want to do the right side. And so I will do this exact thing that we've done before, where I will start all the way on the right with this 1 by 1 by 1 tensor that I have filled with 1. And then I will just recursively go from side n all the way to the first side and compute the one next side over. So if I look back at the contraction, I will just recursively do this contraction all the way from the right until I'm at the first side. In the interest of making things efficient, I'm storing all of the intermediate values, and this will become obvious in just a second because I will need them in a second. And so then I will start my sweeping scheme. So for every sweep, I will go from left to right. And what I will do is I will locally solve the effective equation that I ended up with. Keep in mind, I've already computed L. I've already computed R. So all I need to do is solve this eigenvalue equation. Then, after I've done this, I store my new tensor in the current tensor. This is now the optimal local solution. I move my center 1 to the right. And so simultaneously, because I will now have to solve the next side, I need to grow my left environment by 1 side. I need to go 1 over to the right. And so I compute the left environment of I plus 1. And when I say environment, I just mean this L thing that boundary coming from the left. I repeat this. Now I have already computed everything from the right because I've stored it. I've computed everything from the left because I just computed it. And I can just solve my local Hamiltonian, compute the eigenvalue equation, find the lowest energy state for that, and continue like this. And I sweep all the way through my lattice, going from left to right. Similarly, when I end up at the right-hand side, I can, of course, reverse the order of operations. Everything is symmetric. So I solve my last side. I move my center 1 to the left, and I compute the right environment now. I don't have to recompute my left environments ever because, well, I stored every of the intermediate values, and so they're still in memory. And so I can just obtain the left environment at the ith side, the right environment at the I plus 1 side, build my local equation, and solve it. And so finally, I can do a little bit of bookkeeping to print a bit of information, stop once my energy has sufficiently converged. And this is the entirety of DMRG. And so after a little bit of helper functions, I want to kind of appreciate the idea that this is a function of, let's say, 25, 30 lines. This entire method, which fuels a whole research area, fits in an explanation of about an hour. I think this hopefully gives me, if I save this, wait for just a second while things are loading. So that is the entirety of the algorithm. And so now we can have a look and see how does it compare to the exact free fermion solution that we can compute analytically, and how these values change the results. And so, okay, we're there, nice. First things first, in 2 sweeps, well, after 1 sweep, actually, the energy is kind of completely converged. You can see here, this is the exact analytical energy. After 1 sweep, I've completely converged. After a second sweep, I'm changing the 16th digit, but that's about it. Of course, I'm only looking at 10 sites, so let's increase this a little bit. Let's bump it all the way up to 100. Oops. In the meantime, it computed 35 sites. And so after order of magnitude 10 seconds, I can do 11 sweeps, where you can see that even after the first sweep, the energy has basically already converged. And so this is this magical DMRG algorithm that really just by doing this simple idea of I locally solve something, I locally find an optimal solution and then move on, I have managed to find like 100 site ground state on a laptop in order of seconds. And so you can kind of see the energy error after one step is already optimal. So one thing you can do here is, well, because you have access to large system sizes, you can start asking questions about thermodynamic limits. And so in particular, I mean, you don't care ever about 100 sites. You care about the limits of what happens if I go to 1,000 sites, what happens if I go to 1,000,000 sites. And so something you can do is you can just, like do an extrapolation in system size. And because this function, DMRG, this algorithm only linearly scales in how many sites you have, you can see what's going on there. And actually, again, for the thermodynamic limits, there's an analytic solution. And so you see that the analytic solution is -4/pi, and as the system size increases, we're approaching that value. Right. So then finally we had like a question before, which is basically what I'm doing now is I'm fixing the bond dimension from the beginning. So I'm saying from the beginning, this is the accuracy that I'm going to obtain. And really, there is not a single point in this algorithm where I did any truncation where I had the ability to change this, right? So I locally solve my equations, I solve them exactly, and so I will, in the end, find the optimal matrix product states of a given bond dimension. This is not very convenient because in general, you don't know in advance how large your bond dimension will have to be. Because you typically say, well, I want something up to a given tolerance. I want something up to a given accuracy. And so one way that this has been extended, and like this is the standard way of running DMRG, is basically, what if instead of focusing on one side at a time, we just focus on two sides at a time? And so you can play the exact same game. Instead of now solving the optimal solution for a single side state, you project onto a two-side state, merge these things together, find the optimal solution there, and then truncate back down at the end. And all that's happening is your local effective equation looks a little larger. You can implement this entire thing if you want. I will just copy paste my solution here, if I find it. Oops. And this looks very similar to what we had for the two-side gate application. I'm going a little quickly here, just so I don't make you stay here until 7. Basically, we write down my two-side MPS state. I solve the local equation for these two sides. And then I truncate the results back down with an SVD. And then I move the gauge to the left or to the right, depending on which direction I'm sweeping in. And so then you can use this, and I will again just fill out the same algorithm. The DMRG implementation is about equal, with the one difference that you now don't run over all sides, you run over all bonds. So that's from I to from I is 1 to n-1, and you do a two-side update at every time, but otherwise everything is kind of the same. And you can, again, play with max bond dimensions, and as soon as this finishes, we'll get some more plots. What's interesting to note here is that actually most of the waiting time is just Julia compiling this function because it's appeared for the first time. And then the second time it will be a lot faster. I hope. There we go. So what's going on here? I have the exact same algorithm. I have one less sweep. This epsilon is the truncation error, which is absolutely tiny. And someone explained to me why the truncation error of the first two sweeps is 0. Here we have an IV. I will give you a little bit of a hint. I have set, I've started from a random state with bond dimension 1. So I'm starting from a product state. I've set my maximal dimension to be 32. So then what happens in the first sweep is I do a two-side update, and what is the maximal dimension that this can grow to? It is 2 at the edges. And so as you sweep, everything can only grow with the factor of the system size, and it just takes a couple warm-up sweeps before you actually reach any bond dimension where truncation is happening. So this is just the truncation error is 0 because we're not truncating. And we can play this game a bit more, like if I increase the bond dimension, it might need another sweep, but I'm not sure. So, yeah.
So does it mean even for bond dimension 2, we get such good energy? Like this is 100-side system, right?
Let's see. Let me see what happens.
Because the first 2 sweeps, it was already very close to the actual energy.
Yeah. So the bottom line of this entire thing is that I'm completely cheating by having a look at the transverse field Ising mod, which at the exact point where I'm looking at is very gapped. What does that mean? It means that the correlation length is very large. It's very small, sorry. And so effectively, because the correlation length is very small, things that are happening very far away don't actually affect anything. And so at the beginning, when I'm optimizing over my single site, even though all of the other sites have not converged, this mistake, this error, doesn't actually affect my local computation. And so after 1 or 2 sites, you've basically optimized the entire thing. And so here you can see if I set my bond dimension to 2, my truncation error is going up a little. Of course, I'm truncating heavily. But if you look at the actual values of the energy, they're the same order of magnitude. And so this is one of the very nice things about DMRG is that like you very quickly get very good energies. Let me put the bond dimension up a little bit to get a more reasonable thing. So you can look at the profile of the bond dimension, and this will indeed show you like these arches of low bond dimension at the edges and higher bond dimension in the middle. And so once this all runs, I think this is what I have for DMRG. So in summary here, one of the primary differences between single site and two-site updates is the ability to change the bond dimension. And so in general, the two-site update is more expensive. And you can tell this by the fact that the local equation you're solving is actually a factor physical bond dimension larger, because you now consider 2 sites instead of 1. At the other side of the coin is, of course, that you can now adaptively truncate. And in principle, like here, I'm still setting a maximal bond dimension. In a realistic scenario, you would, of course, just set a truncation cutoff. Like you set a tolerance instead of a dimension, and then you can just find the bond dimension that corresponds to that accuracy. On top of that, as it turns out, doing 2-site updates is actually more stable because you're less likely to get stuck in local minima. For 32, let's have a look. So this is DMRG. Are there any questions for DMRG? Yes.
Exactly how do we know we're getting close, or how do we know when to stop that?
Yeah, you don't. In general, so one of the properties that I highlighted at the very beginning is that tensor networks are universal. So what does that mean? If I increase my bond dimension through an exponential level, I will in fact get exact results. And so basically one of the ways that the field tackles this is by saying, well, I will do an extrapolation in bond dimension. And for example, if I increase my bond dimension and the result doesn't change anymore, then I am fairly certain that I have captured the correct state. Of course, everything is numerics. And so we can do a lot of analysis to mitigate the chances of making errors, but we are still doing numerics. Yeah.
Is there any concern with this algorithm of numerical error building up as you like? Because you're constantly doing, you know, pushing things over and doing SVDs and then pushing them back and forth. Yeah. So
yes, although, and actually this is an interesting question in the sense that in normal systems on a computer, this is fine. And the reason is that we're basically, the precision you have on all of these operations is the precision you have on floating point numbers, which is 10 to the minus 16, which ends up not really mattering. What's interesting is that lately people become more and more interested in running these things on GPUs. And on GPUs, it's actually beneficial to go to single precision floating point operations, which are 10 to the minus 6, 10 to the minus 8 precise. And there are definitely cases where our SVDs are not precise enough and we run into issues. So it is definitely something to keep in mind, although in standard use cases, you don't end up bumping into this. Yeah.
Also, this to me the momentum space. I mean, you can transfer the moment into the momentum space and do the DMRG.
You can. This is less common, and the reason for this is actually quite simple. Like if you think about this, why does this work? Matrix product states capture local Hamiltonians, and they capture this very well. Everything that is local seems to work. All of our updates are local. Like everything has some form of notion of locality. If you transform your Hamiltonian into momentum space, in the generic case, you now have a connection between every single mode in momentum space. And so effectively what's going on is that your MPO that you just created for your Hamiltonian will grow with system size. And everything becomes more expensive. And on top of that, you left the realm of local gapped Hamiltonians. So you no longer have the guarantee that the entanglement will follow an area law. And so you no longer have the guarantee that these truncations will not be heavy. So it ends up being the case that people don't do a lot of momentum space things here. All right.
Yeah. In these systems, usually there is a transition in which you have long-range correlations. Does this affect the bond dimension?
Yeah. So if you tune this to exactly the phase transition point, I don't remember my convention, so it might be at G is 1 or G is 1/2. Then in principle, the correlation length explodes, diverges. The thing is that at finite bond dimension, effectively you can't capture this. And so effectively this is renormalizing this infinitely long correlation into a finitely correlated system, and you're approximating this phase transition. As it turns out, for the transverse field Ising model, like even at low bond dimensions, you're still capturing a lot of the physics. But so in principle there, you really have to extrapolate to infinite bond dimension. And in practice, this tends to work quite well. All right. For the remainder of the day, I want to give you a brief notion of one of my favorite things about the tensor network. So this is all going to be incredibly biased. And feel free to call me out on that. So who has heard about or who knows what I mean when I say like, oh, there's a symmetry in quantum mechanics? Who has dealt with this before?
Question?
Yeah.
Can you post the?
Yeah. My bad.
GitHub.
I'm not. GitHub scares me.
I feel you.
That works.
Thank you.
So the idea of symmetries, I mean, it's a very old idea that has appeared in a lot of contexts and a lot of situations. And there's this very like intuitive notion associated to what we want to do here. The idea is very simple. If something is symmetric, that means you can do a transformation to it that doesn't change anything. And so somewhere, if you think about this a little vaguely, that means that like I only need to compute half of the information, and then of course I can just do the symmetry transformation and obtain the other half. Like you can make this really concrete and just be like, if I have an image which has a mirror symmetry, I only need to give you half of the image for you to be able to reconstruct the entire image, right? And so that is kind of the thing that we want to do here. So the idea is that, like, what does that look like in the context of quantum mechanics? Well, a symmetry operation means that I'm doing a transformation on my system. Doing a transformation on my system, like in the context of quantum mechanics, just means, well, I'm doing a basis transformation. I'm applying a unitary. And so the entire point of a symmetry is just saying, I have some unitary that I can apply. And if I apply this to my ground state, any observable that you measure on it will not change anything. This is, of course, a restriction, right? Like not all states have this. And in particular, if you look at the states that have this property, the fact that something is symmetric basically means that the symmetry property is preserved in time. And you can then show that this exactly means that that the Hamiltonian, which is the generator of time evolution, has to commute with the symmetry operator. And so, yeah.
Are we just interested in the unitary symmetries because?
I am just interested in unitary symmetries for now. Also because we want to keep things a little bit simple, so let's start with unitary ones indeed. And then like the idea is, okay, we have things that commute, and then it's very, very elementary linear algebra to say that if things commute, that means that you can simultaneously diagonalize them. And so they share an eigenbasis. And so the fact that they share an eigenbasis means that if I have some symmetry operator that I have diagonalized, I can split up my entire Hilbert space in different sectors. And each one of these sectors is labeled by how it's by the eigenvalue of this symmetry operator. And my Hamiltonian can never mix things between different sectors. Effectively, that means that I have block diagonalized my Hamiltonian. Block diagonal matrices are absolutely the best for efficiency because, of course, I don't have to deal with the entire Hamiltonian all at once. I can look at each of the blocks separately. And in particular, for ground states, you typically only are interested for the lowest energy state in one sector, and then often you have reasons to believe that the sector is, one with 0 particles or one with half-filling particles. And then you only need to look at the Hamiltonian in this sector. And so you effectively reduced the problem that you had to solve by a factor that corresponds to how many symmetry sectors you had. The simple example, apparently our favorite example, is the Ising model. And the operator that is the symmetry here is that if I do a flip on all of the spins that I'm acting on, then this commutes with this Hamiltonian. And you can check this by, manually computing this, or you can believe me that this is the case. What that means is that this Hamiltonian gets split up into an even and an odd sector with respect to this flip. And basically, this is just saying that there are states that are trivially, that don't transform at all if you apply a flip. And then there's states that get a minus sign if you apply a flip. And so you can see this in action. And here what I'm doing is I'm building, again, using the same machinery we had before, but now with dense matrices to make it a little bit more obvious. I'm building the full Hamiltonian on n sides. I'm sorting all of them by the eigenvalue of my flip operator, and I'm checking what the result is. And so here on the left, you can see the entries of this Hamiltonian in the Z basis, like in the basis that we've been working with the entire time. And here on the right, I've sorted them by first the plus states and then the minus states. And you can really clearly see that if you look at all of these values, they just very naturally form a block diagonal matrix, where the only thing I've done here is I've just resorted all of the entries. And this holds for larger matrices as well. Also, these are kind of pretty pictures. So if you need a new background for your computer, you can play around with stuff like that. Right. So then, I mean, how do we actually make use of this? Well, basically what I'm saying is like we're going to transform all of our operators into this symmetric basis and then just make use of the fact that they're block diagonal. And so after I've diagonalized x, which was my flip operator, of course, x is diagonal, which means that it has the +1 and the -1 eigenvalue, which corresponds to the different eigenvectors. Z now becomes the off-diagonal one, and so this is not symmetric under flipping a spin. Of course not. This is exactly the thing we're after. However, in our Hamiltonian, the only combination that arises is two factors of Z. And so actually what that means is that like anytime something is flipping from a plus or to a minus state, well, the second factor will correct for the thing that was not symmetric. And so the combination of the two is again diagonal. So you can look at these arrays. The X is diagonal, the Z is not, but combining the two Z's, we now again have this block diagonal form that we recover. Of course, you don't ever want to have to sort all of these things all at the same time. And so this is where the real power of TensorKit kind of comes in the sense that the entire machinery of TensorKit is built to just do all of this bookkeeping at the same time for you without you ever having to deal with this. And so the way that this ends up working is you, instead of using complex spaces, you now use graded spaces where you're telling us, oh, these are the various sectors that are appearing. And so in this case, our local space is something which is graded by Z2, meaning it is Z2 symmetric, flip symmetric. And I have one even and one odd sector in this vector space. And I can use this to build my tensors. I don't know if I have them here. And there's of course some libraries to make the operators in this form. And I think, yeah, like you can look at the different operators there. Interestingly, you cannot ask for the Z operator in the symmetric basis because of course it's not actually symmetric. You need two of them in order for them to become a symmetric pair. Yes. Or you had a question or not? Right. So,
quick question. For more complicated symmetries in Z2, do we have to grade it by the irreducible representations?
Sorry?
For more complicated symmetries than Z2, do we have to grade it by the irreducible representation? I saw irreps over there.
Exactly. So the library, like I'm showing off Z2, the library works with finite groups and SU2 and U1, and I'll show a little bit of that at the very end. What's kind of cool is that all of the code that we wrote is not actually making use of the fact that these tensors are not symmetric. And so by just repeating this entire exercise and copying over all of the code, the DMRG machinery just copies over, and then I mean, this is a bit dense and you can look at it in a bit more detail, but I'm running a bit out of time. The code is just the same, and the only thing that is a little more involved is building the MPO. And since we didn't really go in a lot of detail on the MPO, I won't go in a lot of detail now. Just believe me that you can make this MPO with a little bit more effort for any of the symmetries. And so the idea is here that, again, I can, let me hide this for a second. I can run my Ising model computation, let's say on 30 sites for whatever reason I like, either without symmetry or with symmetry. And so the important thing to look at here is that, okay, I'm getting the same energy as before. I mean, everything still works out very well. For the non-symmetric case, this takes me 1.5 seconds. For the symmetric case, I just halved the computation time. And Z2 is the simplest symmetry. The gains, the computational gains you get scale with like if the symmetry group is larger, this benefit goes up. So here's the wall time of these things. 50, okay. What's interesting to note is that if you look at this Ising model, what's basically going on is that as you tune the strength of the magnetic field, you will go from an ordered phase into a disordered phase. And so the interesting part is here is that the symmetry of the ground state can be broken. And therefore, this only works in the symmetric phase, because of course, in the non-symmetric phase where the symmetry is broken, if I impose the symmetry to be not broken, well, what I end up with is a cat state that tries to mimic the symmetry broken phase. And this is a bunch of information that tries to capture that. What does a cat state look like in an MPS? Well, you get exact degeneracies for your entanglement spectrum because it's actually secretly trying to make the plus 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 state plus the minus 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 state, which is a degenerate combination. And so you can see this here by looking at these spectrum values where on the left-hand side, the plus and the circle are completely perfectly overlapping, and on the right, they're not. And so, again, the left is the ordered phase, and the right is the disordered phase. So we had a brief mention of this before. If I go beyond Z2, you can do a lot more. And so one of the paradigmatic examples is, like, let's have a look at a null-Nebelian symmetry, SU2. And so the Heisenberg chain in that context is typically the toy model that people look at. And you can create this with either no symmetry. You can have a look at just conserving the U1 symmetry, which is a subgroup of the total SU2 symmetry. And again, like you can repeat this entire exercise and just have a look at what the runtimes are for these things. And we spend a lot of effort in optimizing this. And you'll see that it is a ginormous increase. What is more exciting even is that actually this way we can, with all of the machinery of dealing with the symmetries, we can also include fermions. And this effectively means that all of the, oh no, I have to Jordan Wigner my entire Hamiltonian to turn my fermions into spins is no longer required. And actually you can work with tensors that naturally encode the anti-commutation relations. And especially like in 1D, this is not a huge deal because you can always Jordan-Wigner. In higher dimensions, doing a Jordan-Wigner transformation becomes a real pain. And so this bypasses that. And this is some of the stuff that we're still working on very intensely. And so one thing here to note is that I think if I recall this correctly, do I have this somewhere? Oops. Comparing the Hubbard's Hamiltonian on a number of sites, if I only have the fermionic symmetry, I have two blocks where the largest block is size 128. Instead, I can also impose particle number symmetry and spin symmetry. And then instead I get 15 blocks where the largest block is only of size 20. And so effectively, if I now need to do any computations, instead of working with this 128 sized matrices, I can work with matrices of size 20. And so again, you can show that like the results are of course the same because all of this is exact, and keeping all of this in mind, the computations become more efficient. And so finally, like I think that is the takeaway of like these last 20 minutes of what I wanted to say is that all of the things that we've done today, if you use decent libraries, and of course TensorKit is not the only one that has this, you should be able to write code that actually just doesn't depend on this. And so you write code that works for no symmetry, you get the symmetry for free. And then depending on the model you're studying, you get a large amount of benefits for the computational cost of these methods.
So what's happening is you have this.
Finally, one important thing to note is that writing DMRG from scratch is very educational. Everyone should do this at least once, and at most once. This has been done. People have spent a lot of time doing a variety of tricks to make this more efficient, to reuse a bunch of computations. It's not that much different from what we end up implementing here. And actually, if you compare the implementation we have here with something like iTensors or the other implementations, you will see that actually the performance should be not far above at all. Of course, if you want to do this for your research, please use libraries that already have this. You can, I mean, I'll advertise MPS Kit, which is built on TensorKit. There's also PEPS-Kit for those who are brave. But you can also use iTensors. I will also mention TenPy as a very decent Python alternative for MPS simulations. And I mean, you can Google around. There's always more stuff. And I think that's the end of my content for today.